So you have a reversible reaction, it's stuck in the sort of dynamic equilibrium, the rate going backwards and forwards is the same, you have a certain amount of reagents left and a certain amount of product that has been formed, and that's frozen in time. There's nothing you can do? No, very much no. There are lots of things you can do, and we call that the Chatelier principle. We can't disturb the equilibrium. We can prod the equilibrium by changing the environment that equilibrium takes place, by introducing this, what we call disturbances, and the equilibrium will, the reaction will react to try to counteract that change we have introduced, and it will shift in a way that counteract that effect and will try to reach another equilibrium position. But the concentration of reagents and products, the proportion of reagents to products determined by the equilibrium constant will not have changed, but the individual quantities of reagents and products will have changed. So what can you do to disturb the equilibrium? What can you do to prod it and get it out of the equilibrium state and see, make it evolve in a different position of the equilibrium? Well, you can add or remove a chemical. It could be a reactant or a product. You can change the pressure and the volume. So, for example, you could, if you have a small reaction vessel, you can end up with a larger one, or if you have a large one with a smaller one, so you can play with the volume pressure of where that reaction is happening, or you can change the temperature. Increase the temperature or reduce the temperature. And all those things will have a different effect in the equilibrium, and it will depend on the type of equilibrium you have and the state, some of them, the state of those reagents and products, where they are solids, liquids, or gases. So let's have a look at our Haber process and see how we can disturb that equilibrium to presumably make more ammonia. Okay, so we've got our reaction of nitrogen and hydrogen to give you ammonia, and we introduce, we play with the concentration of reactants on the products. So what can we do? We can add one of the reactants, and in the first example I've added a nitrogen, so some nitrogen, sorry. So my reaction is in equilibrium, and I add some nitrogen, and that disturbs the equilibrium. And then what the reaction does is that it evolves for more ammonia until a new equilibrium position has been achieved. So overall, the proportion of reagents and products are the same, but the individual quantities, from being here to adding nitrogen and the reaction reacting to consume that nitrogen, has given us a different position equilibrium, which has meant that we now have made more ammonia. Or we could, if we wanted, remove one of the reagents. Let's say that we actually don't want that much ammonia, we want a bit less. So if a reaction is at equilibrium, and then you remove one of the reagents, so there is less reagent, let's say this, in this case, in the second case is the hydrogen, the reaction will evolve until a new equilibrium position is changed, and it will shift left towards to the production of more reagents, and that's what the arrows, the arrow going towards the left means. You remove the hydrogen, the reaction starts reacting to consume nitrogen, ammonia, until you reach a new equilibrium position. Or instead of adding or removing one reagent, you could add one or remove, add a product. So again, we have our ammonia reaction, and we add, in this case, the product, which is ammonia. So the reaction will react towards the left to consume that ammonia until you end up going back to an equilibrium position. So by adding or removing a reagent or a product, we can control whether the reaction shifts right to the product side or left to the reagent side. So what happens if we change the pressure or the volume? Well, we cannot change the individual pressure if you have gases in your chemicals, because that would change the quantity of those chemicals, reagents, or products you have. But what you can change is the size of the container, basically a larger or a smaller container where your reaction takes place. So imagine that you have your reaction in a container of a particular volume, and you decrease the volume. So you make the container smaller. Well, then you increase the pressure. If you increase the pressure and you decrease the volume, that means there is less space for the molecules. So the equilibrium will shift naturally to the side what has the fewer number of gas molecules. So they occupy less space. So changes in pressure and volumes, changes in the size of the container, only affect your reaction if you have gases, at least one gas, and if you have a different amount of gas in the product and the reagent side. So in our example, if we go back to the example of the nitrogen tetroxide, decomposing to give you 2 moles of nitrogen dioxide, those 2 compounds are gases, and one of them would be enough to be gas. In this case, they're both gas, and there are different molecules of gas. You have 1 molecule of N2O4, and you make 2 moles of NO2. So if you reduce the volume, if you increase the pressure, if you put your reaction in a smaller container, it will naturally move the equilibrium towards the side that has the fewer gas molecules, which is in this case the reagent side. And if we go back to our Haber process, here again they are all gases. It doesn't necessarily have to be all gases. You only need one that is a gas, and you need different amounts of gas in one side than the other. But in this case, you've got both nitrogen, hydrogen, and ammonia are gases. Here you have in total 4 molecules of gas, and in the ammonia side 2 molecules of gas. So if we increase the pressure, if we put our reaction in a smaller container with a smaller volume, then it will move towards the product side, because the one that has the fewer gas molecules. Another thing you can change is the temperature. You can either increase the temperature or decrease the temperature. So for Le Chatelier, to apply Le Chatelier's principle, when you are when you're playing with the temperature, you think of heat as another chemical. So if you have an endothermic reaction, an endothermic reaction is a reaction that absorbs heat. So heat is one of the reagents. You need the heat plus the chemicals, the reactants, to make the products. In an exothermic reaction, heat is a product. You produce the products plus a certain amount of heat. So endothermic reactions, heat is a reactant. Exothermic reactions, heat is a product. And you play with the increasing or decreasing the temperature, and it will move the position of the equilibrium as if it was another chemical. So here you've got the reaction of N2O4, and I've got here the plus 58 kilojoules, plus 58, that positive number tells me that's an endothermic reaction. So that means heat is a reagent. So what happens if we decrease the temperature? Well, if we decrease the temperature, what we are doing is removing heat. So if we remove heat, we remove one of the reagents, the reaction will move towards the reagent side, towards the left, to try to counteract that reagent, in our case the heat, disappears. What happens if we increase the temperature? Well, if we increase the temperature, we are adding heat, and because here heat is a reagent, if you add heat, the reaction will move towards the product side to consume that heat, to go back to a new equilibrium position in which you will have more product than in the previous one. And finally, the effect of catalyst. What happens if we play with the quantity of catalyst in the equilibrium? Well, the answer is nothing. Nothing happens to the equilibrium or to the quantities of the chemicals in the equilibrium, but when you add a catalyst. because catalysts help with the initiating the reaction. But once this is not a reaction that is starting, it's a reaction that has already progressed and is stuck in the dynamic equilibrium. The catalyst will not do anything with that. Yes, it will lower the activation energy between the reactants and products, but it will also lower the activation energy by the same degree between the products and the reagents. So the effect is null. Catalyst increase the reaction rate, so what happens is the equilibrium will be achieved sooner than the uncatalyzed reaction, but they will not change the composition of the equilibrium mixture. Once the reaction is at equilibrium, it stays at equilibrium. It doesn't matter how much catalyst you add, because the effect is the same for the reaction going forwards than backwards.